So markets for different goods executed at different timescales have demand curves that are shaped differently. And so this shows three examples of different demand curves, one in blue, one in yellow, and one in pink. And one of the ways that we can differentiate between two different demand curves is through what's called the price elasticity of demand. And what this describes is how a given change in price impacts demand. And so we measure it using this epsilon. I think it's an epsilon symbol. And so the price elasticity of demand is calculated as -1 times the percentage change in quantity demanded given a percentage change in price. And we can evaluate this at different points along a demand curve. So for different values of epsilon, we characterize things differently in terms of its elasticity. So a value of infinity would would describe a place on the demand curve where the price elasticity of demand is perfectly elastic. And what that would suggest is that quantity demanded, varies considerably, even with the same price. That would be a demand curve that's horizontal. A value between infinity and 1 would suggest that demand is somewhat elastic, which means sensitive to price. A value equal to 1 suggests unit elasticity. This means that a 1% increase in price would lead to a 1% decrease in demand. If the value of epsilon is between 0 and 1, that suggests that demand is inelastic, which means that a 1% change in price leads to a less than 1% decrease in demand. And then an epsilon value of 0 suggests that demand is perfectly inelastic, and that means that it's not sensitive to price in any way. So let's look at an example. So this is a perfectly linear demand curve. And we can break this demand curve up into three different segments, A to B, B to C, and C to D. And we can, for each one of those segments, we can calculate the price elasticity of the demand. So again, we have 4 points on this line and 3 different segments, A to B, B to C, C to D. And each one of those points is associated with a different ordered pair of price and quantity demanded. So point A is associated with a price of $50 per unit and quantity demanded of 4,000. Point B is associated with a price of $70 per unit and a quantity demanded of 3,200, and so forth and so on. And what we want to do is fill in the values of epsilon here. So let's look first at the segment between A and B. So remember, the price elasticity of demand is calculated as -1 times the percentage change in quantity demanded given a percentage change in price. And so the percentage change in quantity demanded here is simply the quantity demanded at point B minus the quantity demanded at point A divided by the quantity demanded at point A. So that gives us the percentage change in quantity demanded. And the percentage change in price is the price at point B minus the price at point A divided by the price at point A. So we can fill in those variables with numerical values from our table. And in the top, we get 3,200 minus 4,000 divided by 4,000. So that's 800 divided by 4,000 on the top. And on the bottom, we have 70 minus 50, or 20, divided by 50. And when you do the math here, you get a value of 0.5. And we can fill in the rest of this table using similar calculations. So the elasticity shown for the third row associated with point C, or at least the segment B to C, would be 0.875, and then the price elasticity of demand between points C and D on the demand curve would be 2. So these different values suggest that at different points along the demand curve, you have different levels of price elasticity, right? So when the price is lower, you have relatively inelastic demand. And when the price is higher, the price elasticity of demand is greater than 1, so it's pretty elastic. Okay, let's look at another example here. This is a different demand curve that's nonlinear, but again, we have 4 different points along the demand curve in 3 different distinct segments, A to B, B to C, and C to D. And And we could do something similar here. What we want to do is calculate the price elasticity of demand for each one of these individual segments, A to B, B to C, and C to D. So let's do the first segment, the price elasticity of demand for this curve for the segment A to B is simply equal to -1 times the percentage change in quantity demanded, which would be going from 4,000 to 2,500, as well as the percentage change in price, which would be going from a price of $50 to $70. And what we get is a price elasticity of demand for this segment of 0.94, which is a little bit inelastic. For the second segment, for B to C, we're looking at the percentage change in quantity demanded and the percentage change in price. So again, -1 times the percentage change in quantity demanded from going from a level of demand of 2,500 units demanded to 1,500, and then a percentage change in price when we go from $70 per unit to $100 per unit. And again, we get a value of price elasticity of demand that's a little bit less than 1, so a little bit inelastic, of 0.93. And then for the last segment, we're going from point C to D. The percentage change of quantity demanded is 1,000 minus 1,500 over 1,500. And the percentage change in price is $125 minus 100 divided by 100. In this case, we get a value that's greater than 1, so it suggests some elasticity of demand. So this is our table all filled out. So notice we have different price elasticities of demand at different points along this demand curve at different market prices. So if we can sort of describe this in layman's terms and just note that the price elasticity is not the actual slope of these lines, what this suggests is that at lower prices we have price elasticities of demand that are between 0 and 1, so slightly inelastic. And then at higher prices, we have values of the price elasticity of demand that are a little bit greater than 1, which suggests some elasticity. And so what that means is that when prices are high, a 1% increase in price causes a greater than 1% decrease in quantity demanded. But when prices are low, a 1% increase in price causes a less than 1% decrease in quantity demanded. So I want to highlight one particular type of demand curve here that's perfectly inelastic. So we can calculate the price elasticity of demand here, and it would give us a value of 0. So what this means in layman's terms is that demand is completely insensitive to price. No matter what the price is, the quantity demanded is going to be the same. So one of the main things that price elasticity of demand tells us is whether a viable substitute exists in the short term. And so in particular, what 0 price elasticity of demand suggests is that there is no reasonable substitute. And this is particularly relevant for one of the main things that we're talking about in this class, which is demand for electricity, right? Demand for electricity is a constraint in many cases. What would we do without electricity? Certainly not use the internet, and that would be extremely problematic. It's difficult to think of. So wholesale electricity markets, which we haven't talked about, but we will extensively over the next couple of weeks, are a good example of a supply curve interacting with an inelastic vertical demand curve. And what that means is that our collective demand for electricity is pretty insensitive to price. You can sort of ask yourself, do you think about it? Do you think about the price of electricity when you go to turn the lights on? Or to use your washer or your dryer or to cook something, and you don't. We're sort of divorced from thinking about the actual cost of electricity in our daily lives and what that effectively means on larger scales in wholesale electricity markets is our collective demand for electricity is treated as a constraint. It is insensitive to price. So we will talk more about wholesale electricity markets later. For now, just know that you and I don't really directly interact with them. So wholesale markets are where utilities are sort of buying and selling electricity from each other. And utilities then would deliver that electricity to us on on our behalf. So we can sort of think about it in a simplistic way as the flow of electricity going from wholesale markets to utilities to retail customers, and the flow of money going the opposite direction. So demand for electricity varies all the time. It varies on a seasonal basis. It varies on an hourly basis. And this figure in particular shows how electricity demand can fluctuate on an hourly basis in the summertime in a southeastern state, sort of like North Carolina. And what we see, every one of these big humps represents effectively a 24-hour period. And those big humps are associated with peak demand periods, and the valleys are associated with off-peak demand. So in the summertime, when we'd be experiencing peak demand would be the middle part of the day, 2, 3, 4 p.m., when everybody's using their air conditioner. Off-peak periods would be associated with periods during the middle of the night where our cooling demands and our electricity demands in general are considerably lower. So if we want to look at how we might estimate the wholesale price of electricity in a competitive market, and don't worry if this doesn't make a whole lot of sense now, we'll get to it later on, there would be some sort of system supply curve that might kind of look like what we show in pink or red here, and it would be interacting with a vertical, perfectly inelastic demand curve. So our collective demand for electricity would dictate how much electricity needed to be supplied. And so that vertical demand curve would be intersecting with the system supply curve, and we would get a market price that's associated with the value on the y-axis that corresponds to the intersection between the system supply curve and the vertical demand curve. And vertical demand in this case is shown right at 10,300 megawatt hours. So that's how much electricity is demanded in this off-peak or low demand hour. We can also look at how prices change during those afternoon hours in the middle of the summer when everybody's using their air conditioner. So quantity demanded goes up, which means the vertical, perfectly inelastic demand curve shifts outward to the right. And it increases to about 17,000 megawatt hours. And so as a result, we are moving along the system supply curve needing to access more and more expensive sources of electricity. As a result, the intersection between the perfectly inelastic demand curve during a peak hour intersects that system supply curve at a higher point along the y-axis, and the market clearing price increases from about $30 per megawatt hour all the way up to about $80 per megawatt hour. And so that's, if you've ever heard people talk about peak and off-peak prices for electricity in wholesale markets, that suggests that prices are going up and down all the time as our demand for electricity goes up and down all the time. Okay, that's it. This was kind of a short lecture today. Next time is our final episode in the Finance and Economics Bootcamp. We're going to do a recap of everything we've learned so far and try to bring it together in an exercise that's going to look a little bit like the midterm. Just note that homework 2 has been assigned. All right, see ya.